Hello, students. Welcome to the physics classroom. Today, we are going to discuss kinetic energy, which is also called the energy of motion. Now, first of all, we'd like to see the connection between energy of motion or kinetic energy and the work concept. Remember, we start with learning what is work, and we learn that work has to do with force times distance. If you push something through some distance, then you do work on the object. Now we have to see the connection between kinetic energy and work so that we can interpret the two. All right, first of all, we have to understand that an object in motion is capable of doing work. An object in motion is capable of doing work. I hope you are aware of what happens when maybe a ball which was in motion, so a ball in motion, and then maybe it finds a cone or maybe some object here that is standing here. When the object hits this object, it has the ability to push it through some distance. So it can actually drag it through some distance. In so doing, we say that the moving ball has done work to this object. So an object in motion is capable of doing work in this case because this object in motion can actually move this other object through some distance and thereby doing work. That's what work stands for. All right, so what we say, maybe to make things a little bit simpler, an object in motion has kinetic energy. So we can say an object in motion has kinetic energy. So that's what we can say. An object in motion has kinetic energy. Remember, KE stands for kinetic energy. Without proof, we are going to actually give the formula for kinetic energy. Kinetic energy can be found by multiplying half the mass of the object and then velocity squared. This is the formula that we use to calculate kinetic energy or energy of motion. Now, let's see. We are still looking at the connection between work and the energy of motion, work and kinetic energy. We see that when a force acts on mass through some distance, an object gains kinetic energy. I think you have observed that one. Let's see this one. We have observed this before. When a force acts on a mass, acts on a, let's say an object, acts on an object, what do we notice? So acts on an object through some distance. An object gains kinetic energy. So an object gains kinetic energy. This statement is something maybe you haven't seen before, but what it says is that there's a connection between the work you do and the energy gained by an object. Let's try to visualize this statement. Again, my surface, and I have my mass is here, an object is here, and then to do work, I have to apply a force on the object. Let's say I start from rest, 0 meters per second, and then I push the box to maybe some distance. Okay, so this is the distance D. I don't know how much it is, but there's a distance D there. I write my D carefully, D, and there's some velocity here. okay, velocity, the mass is here. So what we are saying that the work that is done to the object, the work is actually, remember, the work that is done to the object, if this is the only force acting on, this is the only force. So only force, or I should say the net force, or only force in the horizontal direction. That's what I want to say. This is the only force in the horizontal direction. Then the work done will be force times distance. All right. Now, what I'm saying that this statement, what it says is that the work done will turn out to be the gain in kinetic energy. So this will be actually kinetic energy gain. So kinetic energy gained. So in this case, the kinetic energy gained will be what? It will be just 1/2 mv squared. But by the time I see the box here, it will have the energy 1/2 mv squared. Right? So this formula is valid here. It says the work done by this only force is equal to the gain in kinetic energy, which is actually 1/2 mv squared. All right. And now we can also think about, this is like speeding up or gaining speed or gaining kinetic energy. We can also have an example whereby the crate, once it was in motion, now it slows down to rest and think about what goes on. So this situation says that the crate was in motion. Maybe let's say it was here, mass m. Eventually I see the crate here, mass m, but maybe it had some velocity here, which is not 0, but then slows down to 0 meters per second. For this to be possible, then there has to be a force in the opposite direction. Maybe this force could be force due to friction, for example, right? And we see the crate moves through some distance d here, some distance d. Then we can do the same thing. What's going on here? We see that work actually is done on the object. And as you can see, it's negative work because the force is opposite to the direction of motion displacement. The object is going to the right, but the force is in the, so there's a negative work, and this negative work turns out to be the energy. I mean, it turns out to be, it has an influence of reducing the kinetic energy of the box. So we can do the same analysis or the same idea. Remember, what we said here was that the work done by this force is the equal to kinetic energy again. So here we are expecting to see that the work done has to be lost in potential energy. So work done must be equal to kinetic energy loss, right? So if I multiply the force times distance, if I take the magnitude of the force, I don't want the direction, just the magnitude. Then the magnitude of the force times distance will give me the kinetic energy lost, All right, so this will be the case because this will be my work, but the amount of work that is done by the frictional force must be equal to the loss in kinetic energy. All right, so let's think about different forces. Maybe one force is acting to the right, another one acting to the left. Then what's the connection between work and kinetic energy? We don't want to be talking about losses and gains, but we just want to have this one giant formula that can help us to understand the connection between work and the kinetic energy. All right, so that takes us to the what we call the work energy theorem. Work energy theorem. That takes us to the work energy theorem. The work energy theorem helps us when you have multiple forces. So we are assuming that we have multiple forces acting. When multiple forces act on an object, Then we say that the net work, we don't just say the work, but network, because now we have multiple forces. So the network happens to be equal to the change in kinetic energy, right? Or you can write this as W net is equal to delta KE. So this is called the work energy theorem. It says that the net work done will be equal to the change in kinetic energy. As you can see, if the net work is positive, the change in kinetic energy is also positive, means that the object will gain kinetic energy. If the net work is negative, then we know that the change in kinetic energy will also be negative, and that means there'll be a loss in potential energy. But I will have so many examples to understand this, but it's nice to break down this formula as follows. The net force, we write it like this, times distance, this is times distance, is equal to kinetic energy final minus kinetic energy initial. And we can also break down this further to say that the net force times distance is equal to 1/2 mv final squared. Remember, the kinetic energy is 1/2 mv final squared. All right, and then minus 1/2 mv initial squared. That would be the connection amongst these variables here. What it means is that the network is equal to change in kinetic energy, and this is also the work energy theorem. We have examples in which we can apply the work energy theorem. So let's look at examples. All right, example 1. Example 1 relates to an object sitting on the surface, and we have two forces acting on the object. This is 2 kilograms. There is a 5 Newton force acting on this object, 5 Newton, and there's a force backward that is 2 newtons. Of course, there is gravity, there is support force, but I'm focusing on these forces. So of course, there's gravity, and normal force or support force. Normal force or support force. These forces are there, and the box moves through some distance. So from here to some position here. So this is a new position of the box, and this is 2 kilograms. All right, so what I'm seeing here is that the velocity here, I'm told that velocity is 0 meters per second, and the velocity here is 2 meters per second. The question is, what is the distance here? If there are these forces, multiple forces acting on the 2 kilogram object, the object accelerates to some speed, 2 meters per second later. The question is, what is the distance that the object has actually moved? Now I see here that I can apply the work energy theorem. The work energy theorem tells me that, let me use a different color. The work energy theorem tells me that if I multiply the net force times distance, the answer must be the change in kinetic energy, 1/2 mv final squared minus 1/2 mv initial squared. Now I realize that the initial kinetic energy is 0 because initial speed is 0, as you can see here. So this part goes to 0. I end up with 1/2 mv final squared. What I need is the distance here. That's what I'm looking for. So I will divide both sides by net force. So divide both sides by the net force. So you can only remain with distance. This cancels with this. So distance traveled will be 1/2 mass times velocity squared and divided by the net force. By the way, we see here that the net force can be calculated because we have 5 newtons to the right and 2 newtons to the left. The support force cancels with gravity. They are balanced up. We only have 3 newtons as our net force. So 3 newtons is our net force. So we can have our answer as 1/2. The mass is 2 kilograms. The velocity, final velocity, as you can see here, is 2 meters per second. Then the net force is 3 newtons. 3 newtons. So everything here will give me my answer in meters. So I make sure that I'm using consistent units or SI units. If I'm using SI units for each variable, then it's okay to drop the units and just put the meters here. All right, so if you try to work on that, you'll find that distance will just be 4/3 of meters, or you can say 1 and 1/3 meters. So that would be the distance traveled. Here is how we apply the work energy theorem to solve problems. We are able to find the distance traveled given the net force and the final velocity. Okay, let's look at example number 2, in which we can apply the work energy theorem. Example number 2 relates to distance as well. So this one is slowing down situation. Slowing down. Let me see. I want to draw a good line. Okay, see, I can draw a good line sometimes. Okay, there. And okay, can I do that? Okay, as usual. This problem relates to slowing down. I have my mass here, and next I see that it's there. I put a dotted line to show that it's the final position, different position here. So what's happening here is that I am applying a force of 2 newtons. So no, this is 4 newtons. 4 newtons to the left, but the object is slowing down. Actually, it's possible, you know. It's possible to have the force acting opposite to the direction of motion. This is possible. Think about when a crate slows down due to friction. It slows down. As it is slowing down, the force direction and the velocity direction are different. They are different. So as you can see here, they're different. And then this slows down to final velocity of 0 meters per second. The question here is, what is the distance covered? What is the distance from the center here to the center of the mass here? What is the distance here? Okay. We are going to apply the work energy theorem as well. We start by saying that the net work has to be equal to the change in kinetic energy. That's what I know from the work energy theorem. The net work is equal to the change in kinetic energy. And net work is the net force, remember, times the distance. And the change in kinetic energy is 1/2 mv final squared minus 1/2 mv initial squared. In this case, the final value goes to 0 because we final velocity is 0 here. So this, everything here goes to 0. Then you remain with minus 1/2 mv initial squared. Now to find the distance, you divide both sides by F net here and F net here. This cancels with that. You end up with distance equal to minus 1/2. The mass, I should have given you the mass. The mass is 2 kilograms. Mass of the object is 2 kilograms. This is no, otherwise we can't solve the problem. 2 kilograms. Well, should I keep the units? No, I want to keep the units this time around. Again, the velocity V initial squared is 2. 2, that's the initial velocity squared. 2 squared, then divide by net force. Net force is here because that's the only force acting in the horizontal direction. So the net force is just 4 Newton, but since it's acting to the negative x direction, we put -4 here. Everything will give us a distance of 1 meter here. And if you do your mathematics, you should be able to get -1 meters. So that will be the distance traveled by the crate, -1 meters. Oh, sorry, plus, because minus is plus. So +1 meters. That will be the distance traveled. Okay, let's see. Okay. Well, what if this is, it looks like trivial, question number 3. What if the velocity doesn't change? So I'm assuming that we have the net force of 0. What is the change in kinetic energy? This problem is asking you to find the change in kinetic energy. So we have our surface here and the box is here. Well, you might know that the mass is still 2 kilograms, but the forces are balanced. There's a 5 Newton here and there is 5 Newton here. Question is, what is the change in kinetic energy? If you see this kind of situation, the velocity right now, maybe you may be told what is the velocity, but it's moving at a certain velocity, 2 meters per second. So for this problem, the change in kinetic energy is just, well, it's the network. Remember, network is equal to the change in kinetic energy. Network equal to delta KE. And do you see that there'll be change in kinetic energy? I don't think so, because the forces are balanced and the speed is constant. But we can explain this using the work energy theorem, because the quantity here will be F net times distance times change in kinetic energy. Oh, sorry, equal to change in kinetic energy. And the net force, because you have 5 here, 5 here in the opposite direction, it's just 0 newtons. 0 newtons times no matter what distance you might move. I don't know what distance you might move, doesn't matter. But you realize that 0 times D will be 0. So the change in kinetic energy is actually 0. So 0 joules will be the change in kinetic energy. So the change in kinetic energy is basically 0. In other ways, kinetic energy is constant. So here it says that kinetic energy is constant or does not change. Kinetic energy does not change. Does not change. Or some people will say kinetic energy is constant. Kinetic energy is constant. In this case, the work energy theorem tells us that the work done by the 5 Newton force is equal in magnitude to the work done by this. So the network is 0, and therefore the object keeps on moving at the same speed. We are going to finish our discussion by looking at stopping distances. I hope it will be enough space to talk about stopping distances. All right, so the next 3 slides, we have 3 slides. We are looking at the stopping distances. Now, stopping distance. This is a common question when a car breaks, the car wheels get locked, and then you see skidding. We have skidding that takes place during that time. The question is, what is the connection between the stopping distance and the initial velocity of the car? So I'm trying to draw the car here so I can try to explain what I'm trying to say here. So this is the car here, and the car is moving. And right now, it's moving at a certain speed. We call it V. Okay, V. And my worry is, so let's say this is V initial here. My worry is what would be the stopping distance compared to some speed, for example. Start from V initial, and then I end up with maybe here, I end up stopping V final, 0, I stop. Now there is a distance here that's called stopping distance. So this is a stopping distance. Stopping distance. Now, the question is, what if I double the velocity that I start with, maybe VI to twice VI? What will be the stopping distance? So let me do this. Yes, something that we need to think about carefully here, because it's very important. If you think about application of the work energy theorem to everyday life. So maybe I don't want V, but now let's say the car started slowing down when the velocity was twice VI. Then what will be the stopping distance in connection? So distance will be how much? I want you to compare that, compare with the distance here. So this distance 1 and distance 2. How does this compare with distance 1? How does it compare? That's the question we should be answering. When you are skidding to a stop, the brakes or the wheels are locked and the wheels are not rotating anymore, that means the car will be skidding to a stop, right? Does that depend on how fast you are traveling initially? That's the question. What's the relationship between the stopping distance and the velocity that you had when you started slowing down? That's the question. We are going to answer this question by looking at a few things. We have to remember the work energy theorem. The work energy theorem tells us that, let me see if I can use, it tells us that the network is equal to change in kinetic energy. So network must be equal to change in kinetic energy. Okay. And this implies that the network will just be the friction, because remember, during the slowing down, our force is actually acting in the opposite direction. This is a stopping force, and this is a stopping distances. So what we are saying is that the network will be just the stopping force, F, then times what? Times, we have to multiply, we can put a minus to show that it's negative, minus F there, and then, let's see, we can just put the force in the X direction, and then we are going to talk about direction later. Force in the X direction, and then times distance, stopping distance D, right? So D1, this is the stopping distance 1 here. Then that must be equal to change in kinetic energy, which is 1/2 mv final squared minus 1/2 mv initial squared. Now, since the final speed is 0, this goes to 0. We are going to end up with the force in the X direction times distance 1 is equal to minus 1/2 mv initial squared. So this is the relationship between this force, stopping force, and distance. All right, okay, now let's see. We are going to look at experiments and what experiments show us. So let's move our formula here. So the force in the X direction is actually the force due to friction. So we're saying that the force due to friction times the distance gives us negative 1/2 mass times v initial squared. This is the initial velocity before the object starts skidding. This is our frictional force. Actually, this one is a frictional force. We have to talk about direction later. When we put in the numbers, we put in the direction, negative or plus, but we know it's negative. But that's just a frictional force. With could be negative or plus, but it's negative. And that's the stopping distance. Now, experiments have shown that, I want you to understand this. Experiments have shown that the maximum friction, the road can supply to a skidding, okay, to a skidding tire is nearly independent. Independent of initial velocity. So in other words, what you are saying that the force of friction here is it's the same, it's nearly the same, whether the car skids from fast speed or slow speed. I'm thinking about this situation. Remember, it all starts here. The frictional force here is the same. This one and this one happens to be the same, whether the car is moving slow or fast initially. So experiments have shown that this value of F is actually the same. Mathematically, this tells us that if this is constant, this is constant, this is constant, then the only thing that matters is the distance and the velocity squared. These ones are the ones that will be related because the force is constant. Mathematically, this means that we can say distance is inversely proportional to initial velocity squared. This is what I wanted to actually to focus with you guys. This should be constant. That's very, very important. Now, what it means is that distance is proportional to initial velocity squared. Okay. So when you are driving, for example, at 45 kilometers per hour, how much more distance do you need to stop compared with driving at 15 kilometers per hour? Imagine you have that question and you want to use this idea. How will you respond to that question? So when you are driving at, let's say you are driving at 45 kilometers per hour, how much more distance do you need to stop? We are comparing with the compared to what? Compared with driving at 15 kilometers per hour. Driving at 15 kilometers per hour. So this is the question that you can answer using these ideas here. Would like to use this idea here, that the stopping distance is proportional to, or maybe we should write it, this is proportional to, so weekly sign means proportional to V initial squared. Using these ideas, or using this important idea or result, when you are driving at 45 kilometers per hour, how much more distance do you need to stop compared with driving at 15 kilometers per hour. One thing you should see here is that the speed is actually, the speed is tripled. If you compare the original speed and the new speed here, the new speed is triple, it's 3 times the old speed. So what will happen to the stopping distance? Well, you might say VI goes to 3 VI, then VI squared goes to 3 VI squared, and this gives you 9 VI squared. So we see that VI squared goes to 3 VI squared, and this will be 3 squared times VI squared. It's 9 V initial squared. That means our stopping distance will be 9 times more. When you triple the velocity, then what you are saying is that the distance will be 9 times more. The stopping distance will be 9 times more. That's what it means. You can also try this. What will happen if you double the speed? Like the example we had here, we haven't answered it here. From V initial to twice VI. What will be the stopping distance here? I'd like you to try that. What will be the answer? What will be the stopping distance in connection to D1? What will be the answer? So I want you to apply the same reasoning as the reasoning we have applied right here, because here we found that when we triple the speed, we multiply the distance traveled by 9 times. I have also one way to solve this problem, another way to solve this problem. The other way is to think about the mathematical understanding of proportional. When we say direct proportional, what does it mean? So the other way is to do this. You can say, okay, distance is proportional to V squared, V initial squared. Okay, what does this mean? It means that distance divided by V initial squared, this is always the same, is constant. That's what it means. It means anytime you divide distance, stopping distance by V initial squared, the answer is always constant. That's what it means. That's what it means when you say directly proportional to VI squared. That's mathematical understanding of proportionality. That means if you know distance now, maybe odd, the one in the velocity initial, this one, let's call this one 1, square that, it will be equal to the distance 2 divided by V initial, then this one will be 2 squared. All right, so you have V initial 1 squared, V initial 2 squared. Then you can actually, I might have to remove the initial to make your life easy. Let me remove the initial to make your life easier. We know that is initial velocity of the vehicle, but we can make life easy by just dropping it. So constant, or let's just say distance over V is equal to constant. Okay, over V squared, sorry, constant. That will be good because we have subscripts to deal with. We have to forget about the I. Now, distance over V squared is constant. What does that mean? It means distance 1 over V1 squared has to be distance 2 over V2 squared. So the 1 is when the speed was 15 kilometers per hour. The 2s are when the speed was 45 kilometers per hour. That's what you are trying to say. So what you are looking for is the relationship between D2 and D1. So we can write that D2 from here. If you find D2 will just be, if I want D2, it will be V, let's see, it will be V2 squared divided by V1 squared, then times d1. This is actually what it means. And you can also say that d2 is equal to, I'm going to rewrite this part to make it v2 over v1, then everything squared, then times d1. Okay, now we know that v2 over v1, we can find it because now d2 will be, what was v2? v2 was the velocity, 45 kilometers per hour. v1 is 15 kilometers per hour. This is v2. So go back there and substitute. v2 is 45 kilometers per hour. v1 is 15 kilometers per hour. Then everything squared times d1. This gives you 45 over 15 is 3. And this is 3 squared times distance 1, original maybe. So this gives you 9 times d1. So what you are saying is that the new stopping distance, is equal to 9 times the odd stopping distance. All right. Since velocity is squared, then yes. Since velocity squared is 9 times more, stopping distance is 9 times as well. Okay. You can also say that to make your life easy. You can just say, well, we already did it here. Let me go back. If you don't like the mathematics here, if you don't like this one, you can just say, I go back to this one. You can just say, since v is actually tripled, velocity is tripled, then v squared is actually 9 times more, then the distance will be 9 times more. All right. So to answer this question, when you are driving at 45 kilometers per hour, how much more distance do you need to stop compared with driving at 15 kilometers per hour? The answer is 9 times as much distance. All right. So the question you have right here, I will leave you with a question, is this one. This is the question which is unanswered. When you are driving here and if we double the speed, what would be the stopping distance? Let's say you were moving at V initial, maybe 15 kilometers per hour, then you come to a stop. You have a stopping distance D1. Now you double the speed at which you started the skidding. Now the twice VI, how much more will you stop compared to this first stopping distance? Will it be 2 times, 3 times, 4 times, 5 times? So I want you to figure out what is the response to this question, okay? So I'll stop here. If you have any questions, please let me know. I'll stop here. You might have to go back to the slides, watch the video again to try to make sense of the discussions we've had here. Thank you so much. I wish you all the best. Bye.